I hope you had time to look at the table that summarized most of the transformations we're going to look at. It had a lot of stuff, but I hope you noticed they were mostly in pairs. So we're going to explore those and one more. If you have colored pencils, that will help. You want to pause and take time to get them now? That might be a good thing. So we're going to be working with functions and using the function notation. By outside changes, I mean we're going to be doing literally stuff that's outside the f of x. Things like f of x plus 2, the opposite of f of x. 3 times f of x. These things that are outside the f of x, they change the y values. And a lot of us have learned to think of f of x as just like the y's. If the changes are done inside the f of x, that means we're affecting the x's, the input values. But the outcomes are going to stay the same. So that would be something like f of x plus 2, f of the opposite of x, f of 3x, where the changes are done to the x's on the inside of the function, and then we do whatever the operation is that the function prescribes. Our first type of transformation is going to be reflections. If we reflect a graph across the x-axis, the horizontal axis, we can represent that as y equals the opposite of f of x. Whatever the y values are, we're going to change them. And you've known for nearly a third of your life what this means. Y equals negative x squared. That we can just take the graph of the parent function and flip it across the x-axis. It just turns it upside down. These happen to be all positive or 0. The opposites are all negative or 0. That's it. So how about if we have y equals negative x cubed? So I'm going to draw the parent graph, which I'm sure you remember. There's this little zigzag here. So that's the parent function. And if we reflect it across the x-axis, this part's going to flip up here, and this part's going to flip down here. So this would be y equals the opposite of x cubed. All the y's get reversed. The negative ones become positive, positive ones become negative, but the x's stay the same. We also have reflections across the y-axis, which means we're going to be flipping the things sideways. And that's going to be y equals f of negative x. Because if we're flipping sideways, what used to be a positive x is going to become a negative x. Negative x's are going to become positive x's. So how about y equals negative x squared. Instead of negative x squared, It's the opposite of x and then square it. So the original parent function and then when we flip it sideways, then this flips over here, this reflects across to here, and this actually looks the same. Sorry about the heater's noisy. Which it is. When we square a negative x, we're going to get the same answers as when we squared a positive x. This is what they call an even function, and Mrs. Milburn will talk more about this later. One more. Suppose y equals the square root of negative x. I know we've been taught that you can't take the square root of a negative number, but maybe when we do the reflection, it'll make sense. So the parent function is y equals the square root of x. It's like the top half of a sideways parabola. And then if we reflect this across the y-axis, I messed up. Sorry, it's supposed to be the square root of negative x in there. Well, if we try 1x is 1, and we should often try to see if what we've done is right. If x equals negative 1, then y would equal the square root of the opposite of negative 1. So it will work because we're going to be putting negative x's in and taking their opposites, so we'll end up being able to take the square roots after all. And that's all reflections that we're going to study today, just across the x-axis and across the y-axis. Next, let's consider translations, which you may remember from geometry were called slides. With transformations of functions, it's not going to be exactly like geometry. When we start changing the way the values of a function are calculated, it won't be as simple as just sliding a triangle around. Suppose f of x is the absolute value of x. And we let y equal f of x plus 2. So that's just going to be y equals the absolute value of x plus 2. What do you think is going to happen to the graph? I mean, you know what the absolute value graph looks like. What do you think is going to happen to the graph in your head? What's your prediction? Well, let's check it out. So if we have y equals absolute value of x plus 2, and we have x, we make ourselves a little table, and we put in a 0, and a 1, and a 3, and a negative 1, and negative 2. So we put in a 0 and add 2. We put in a 1, take its absolute value, add 2. Put in a 3, take its absolute value, add 2. Put in a -1, take its absolute value, and add 2. Put in a -2, take its absolute value, and add 2. And just making a rough sketch here. So we know the original parent function has a graph like this. But this one's saying go across 0 and up 2. Go across 1 and up 3. Go across 3 and up 5. Go across -1 and up 3. Go across -2 and up 4. So this one did get raised, and this was supposed to be a 1 and a 2 there, did get raised 2 spaces. Took the original function, original parent function, and just raised it up 2 spaces. Was that what you predicted? How about we try another one? If we have y equals x cubed minus 2, what do you predict is going to happen? Just going to make another rough sketch. So I know the original y equals cube root of x looks something like this. And then we're just going to drop everything down 2 spaces. Sorry about my drawings. So it's going to look like this. Just dropped down 2. This was the original y equals x cubed. So that's pretty easy. And that's a lot like geometry. In general, if c is greater than 0, where c is a constant, it's not going to change, it's just some number, then y equals f of x plus c is just going to make the graph go up c units. And if we have y equals f of x minus c, the graph is going to go down by c units. Pretty straightforward. So now, what's your prediction? If we change the x's, if we have y equals f of, say, x plus 2, what do you think is going to happen then? Well, let's try it for, we did it up here with absolute value, so let's try it with absolute value. Where the 2 is with the x inside the bars, one of these inside functions. And we'll make a little table. So when x is 0, 0 plus 2, take its absolute value. When x is 1, 1 plus 2, take its absolute value. When x is negative 1 plus 2, take its absolute value. When x is 2 plus 2, take its absolute value. When x is negative 2 plus 2, take its absolute value. When x is negative 3 plus 2, take its absolute value. And we try to sketch the graph. Well, the original absolute value graph is supposed to look like this. And according to our table here, 0 for x is going to have a 2 for y, and 1 is going to have a 3, and negative 1 is going to have a 1. And 2 is going to go across to 4, and negative 2 is going to be at 0. And negative 3 is going to be at 1. Now you probably expected that changing the x's was going to move the graph backwards and, left and right, rather than up and down. But did you expect that it would move it to the left? It looks like we should add to, move it to the right. When we're dealing with functions, if you change the inputs, it's going to be the reverse of what you would expect. The x's are going to have to compensate for the fact that you're changing the input value. So if we get one of those lovely late openings where school is delayed for 2 hours, that means we can kick back for 2 hours and move back our starting get-up time by 2 hours. If school's going to advance by 2 hours, we can compensate by going back to bed for 2 hours. It happens. So let's try another one. Let's try y equals 1 over x minus 3. Now, if we left off the minus 3, I'm hoping you'll recognize that that's the reciprocal graph and that you'll remember its basic shape. So in the reciprocal graph, the parent function looks sort of like this. Got asymptotes at x equals 0 and at y equals 0. And if I'd done this right, there should be a point right here at 1, 1. Because for the original one, the original parent function is y equals 1 over x is the parent. If we put in a 1, 1 divided by 1, we come back out with 1. Now, it looks like we should move this to the left, but we're going to compensate. The x is saying, if you're going to take 3 off right away, and I'm supposed to end up in the same place, then I'm going to have to start out 3 larger than I used to, just to get the same result. So this whole thing is going to get moved over 3 spaces to the right. And the graph is going to be, instead of having an axis here at x equals 0, we're going to have an axis here at x equals 3. And the graph will be shaped around that new axis. It's a little trickier to draw. Everything's going to get moved over to the right by 3 spaces. And this space, it was at x equals 1, we moved over to the right, so now it's at x equals 4, but it's still 1 space up. So we should check, really. Will this point, this new point, does it fit in our equation? And the equation was y equals 1 over x minus 3. So if we put a 4 in for x, it does come out to 1 over 1. So y should be 1. It looks like this graph that was slid over to the right 3 spaces does work, whereas sliding it to the left would not. So even though it's a little strange, it's not that hard. In summary, if we're going to translate the x's, if we have f of x plus c, that's going to move left c units. And if we have f of x minus that constant, it's going to move to the right by c units. And this is assuming that c is a positive number. Another type of transformation that you may remember from geometry are dilations, stretches and compressions, or sometimes we call them stretches and shrinks. And instead of adding or subtracting or reflecting, we're going to multiply. Dilations were one transformation that was not rigid. The previous ones we studied kept the same size and shape. Dilations, though, can enlarge the whole shape or contract it. Sorry about the noisy heater. So, if we have y equals a times f of x. Now, this is an outside thing. It's going to affect the y's. It's going to be a vertical stretch. The y's are going to get bigger if our multiplier out there is greater than 1. If we're multiplying by 2 or multiplying by pi. And it's going to be a vertical compression or vertical shrink if what we're multiplying by is in between 0 and 1. In other words, a is a proper fraction. like 1/2 or 2/3 or 9/10. So how about we try y equals, I don't know, 2 times f of x. That's going to generate a graph where the y values are twice as high which you would expect. But what some people forget is the y values are also twice as low. So if we have y equals 2 times the absolute value of x, that will work. Oh, let's make it different. Let's make it y equals 1/2 the absolute value of x. So we should expect then that the y values are going to be half as high as they used to be. Whatever the answer was, we just cut it in half. So the parent function, original graph looks like this. But if we're going to cut all the y values in half, that means when x is 1, the absolute value is only going to be 1/2. And when x is 2, the absolute value is only going to be 1. And when x is 3, it's going to be 1.5. And when x is 4, it's only going to be 2. So the graph, the y values, are going to be only half as high. How about if we have y equals 2 times f of x, and I'm just going to sketch a random f of x here. I'm just going to sketch some polynomial. Looks like a positive cubic polynomial. So then the y values are going to be twice as high, about 2 times 0. Well, that's still 0. And then this is going to be twice as low here. 2 times 0, twice as high, 2 times 0, twice as low here. 2 times 0, twice as high here. So the graph will be considerably stretched. But because the x's don't change, it's still going to cross the x-axis at the same places. It's only the y values that are changing when we put the changes on the outside of the function. How about the x's? If we have y equals 2x and then square it, how is that going to change the original parabola? What's going to happen to it? So if we're changing the x's here, that's going to affect its width. Will this make the graph twice as wide? Nope. Because if you remember, the x's do things in reverse. So the graph is actually going to be half as wide. It's going to reach the same y value in half the time. In general, y equals f of a times x is going to mean a vertical shrink. If a is greater than 1. And it's going to be a vertical stretch if a is in between. Yep. Messed up. Nothing like a little whiteout. If we have some fraction that we're multiplying by, it's actually going to be a vertical stretch. Some textbooks say that if we have y equals f of a times x, that means we actually divide. That is going to be, the y values are going to get, I'm sorry, it's not the y values, the x values are going to get divided. Keep the y values the same. So if we are multiplying by something bigger than 1, this is going to get smaller. If we multiply by some fraction that's less than 1, x divided by that fraction is going to get bigger. So we'll try it with this case here. So the original parent function grows pretty rapidly. I'm not going to fit enough of them on here. So the third one would be way up here somewhere. And I don't think I made this even. I didn't. So this would be our original, our parent function. And the x's are going to compensate. Reverse effect. Like if you are going to immediately double the amount that I'm going to invest, then I only have to put in half as much money in order to end up with the same amount. So the x's only have to be half as large. Well, 0, 0 is still going to stay there, but we can reach this y value with only half as much effort from the x's. We can reach this y value with only half as much effort from the x's. And the same here. And of course I put the numerals in the way, but the graph is going to be only half as wide as the original graph. Now this does look an awful lot like y equals 2 times x squared, but they're not alike. Once you plot the points, you would see the difference. And with dilations, you often have to plot the points. But they are different. When you plot the points, it's easier to see the difference. But that gets tedious. So if we have, say, y equals 2x squared compared with y equals 2x quantity squared. If x equals 3, so y equals 2x squared is going to be 2 times 3 squared, which is 2 times 9, that's 18. This one is going to be 2 times 3 and then square it, which is 6 squared, or 36. Big difference when you put in the same numbers, but it's not so obvious until you actually plot the points. Now, to sketch y equals 1/2 of x squared. That doesn't mean that the graph will be 1/2. The graph will be x divided by 1/2, or x times 2. It's going to be twice as wide as the original was. So the x's do everything backwards. It's wonderful. One last one. The absolute value of a function. This is my favorite because it's literally so positive. It's not the absolute value function. It's not y equals the absolute value of x. It's y equals the absolute value of a function of x. And if you look at that, you may realize that this means all the y values must be either 0 or positive. You can't have any negative y values. So it is literally a very positive function. So how we do it is you sketch the original y equals f of x, whatever that is. And then you keep the parts where the y's are 0 or positive. In other words, they're on or below or above the x-axis. And you flip up, reflect across the x-axis, the parts of the graph where the y's are negative. In other words, the parts that are below the x-axis. So for example, we have y equals the absolute value of x squared minus 4. So first we sketch y equals x squared minus 4. And you know, that's a parabola. And it originally would be above the x-axis, but because it's minus 4, it's going down below the x-axis. I'm going to just drop it down 4 spaces. Now we keep the parts that are above the x-axis or are 0. And the parts that are negative, well, the y's aren't allowed to be negative, because y is going to be the absolute value. So we're going to reflect that up 4 spaces. And we have a very happy graph there. No negative results. So now would you please go do the you try document.